Hello and welcome. Thanks for coming. This talk is going to summarize our JFP paper, Poppelmark Reloaded, Mechanizing Proofs by Logical Relations. My name is Brigitte Pientka, and this is joint work with Andreas Abel, Guillaume Mallet, Alia Hamir, Alberto Momiano, Stephen Schäfer, and Katrin Stark. So today, mechanizations are commonplace in programming languages. However, they're also time-consuming, and there are few design guidelines. So what's the problem? The problem is that, in fact, proofs are tricky to write, both on paper as well as in proof assistance. There are a lot of challenging details to keep track of. On paper, it's hard to keep track of the dependency among different theorems and definitions, and one might think that proof assistance are the answer. But in proof assistance, there's sort of another overhead we have to deal with. We have to build up an infrastructure for modeling, for example, bindings and contexts and so on. So there's quite a lot of time that gets into building this particular infrastructure. It's often hard to understand how different features interact. Difficulties increase with the size of the mechanization, and it can be really quite time consuming. We see this that often a whole team of students is actually tackling some of these mechanization efforts. And experience very much matters. Now, the goal of this paper was to develop a benchmark problem that would allow us to gain a deeper understanding of the similarities and differences in how we mechanize problems in programming languages. Now, we as developers of proof assistance and libraries wanted to make our approaches more robust and identify primitives and abstractions to better structure proofs and bring down the cost of verification overall. So it's worthwhile to take a look back at Poppelmark in 2005. Back in 2005, the Poppelmark challenge was to mechanize system F sub. And this is a problem that can be fairly easily understood. It's described in types in programming languages. It can be mechanized in a couple of hours. It focuses really on representing and reasoning about structures with binders, in particular how we model the polymorphic function space. All proofs were syntactic by structural induction, and it was a great way of exploring different encoding techniques for representing bindings. In fact, people used strings, De Bruijn, nominal encodings, locally nameless, as well as higher abstract syntax. But on the flip side, it did not really identify any bugs or flaws in the existing system. It did not inspire the development of new theoretical foundations, nor did it push any of the existing systems to their limits. All systems were, in some sense, equally suitable. So we wanted to go beyond the Poppelmark challenge, and in fact, one doesn't need to go very far. One just needs to look in the conclusion of this paper, and one sees that one of the problems and challenges the authors mention is proofs by logical relations. So our contribution here in this paper is to describe a tutorial for strong normalization proofs for well-typed terms using Kripke-style logical relations. There are really few standard textbook chapters out there that focus on strong normalization proofs. But although it has been really a gold standard in some sense to evaluate proof assistance using a strong normalization proof by logical relations. See, for example, Thorsten Altenkirch's work in 1993, where he used Lego to give a mechanization of a strong normalization proof for a simply type lambda calculus. Now, one difference between all this work and ours is that we are really focusing on well-typed term representations, and that leads us to a Kripke-style logical relation, where we talk about extensions of typing contexts. And this also brings me to the challenges which really go beyond the original Poppelmark challenge, because we need to model simultaneous substitutions and renamings, context extensions, structural properties such as weakening and exchange and strengthening play a much more central role. And in order to describe the reducibility definition, we need to have a way of distinguishing between inductive and stratified definitions. And last, we implemented our solution in 3 different proof assistants: Beluga, Coq, and Acta. Now, I also want to mention some considerations that went into choosing this particular benchmarks, because there are, of course, many different kinds of logical relation proofs and Kripke-style logical relation proof. In particular, they've been very popular for reasoning about concurrent and imperative programs, where we reason about memory extensions rather than typing context extensions. Nevertheless, we focus here on logical relations proofs for typed terms, the simply typed lambda calculus, no state, but we believe that this is a good springboard for richer theories, in particular dependent type theories. One problem in particular that often comes up when you think about dependent type theories is the notion of equality, and we need to sort of reason about soundness and completeness of algorithmic type-directed equality, and the proof of soundness and completeness of type-directed equality exhibits many of the same ideas and challenges that we have in the proof of strong normalization for the simply typed lambda calculus. And last, our guiding principle was really to design a benchmark that is reasonable, so a grad student should be able to do it after reading the tutorial. So how do we define strong normalization? So traditionally, we define it by saying M is strongly normalizing if all rewrite sequences starting in M end in a normal form. And this is often characterized using what is called an accessibility relation. But in fact, the proofs become increasingly annoying when we need to reason about all these different rewrite sequences and analyze different reducts. So an alternative was proposed by Femke van Raanstonk and Paula Severi, going back also to Gauguin, is kind of a modular approach to strong normalizing, where we have an inductive characterization of normal forms. And this leads to modular proofs, both on paper and mechanizations, and the proofs essentially become much simpler. So the first challenge problem is to prove the equivalence between the accessibility relation and the inductive definition of strong normalizing terms. And the second one is actually proving strong normalization for the simply typed lambda calculus using that inductive definition. And that will have certain subproblems that we also then describe in the paper and outline the proofs. So in the remaining few minutes, I want to talk about our solutions. One, Beluga, which uses contextual higher upstack syntax, and then Acta and Coq, where we used the Bruin encodings. So Beluga is probably the youngest system among these three proof assistants. It supports higher upstack syntax based on the logical framework LF, and therefore it's of course great to model binding structures. Beluga also has built-in support for substitutions and renamings, and in that sense it's kind of ideally suited for that particular problem. But it was also a great case study for finding bugs and make the system more robust. So in particular, it allowed us to find bugs in coverage checking and extend termination checking. And over the last year, we also implemented an interactive proof development mode, Harpoon, to make it easier to develop such proofs in general. But there's no proof automation. Now, Coq, on the other hand, we used the Bruin encodings for modeling bindings. We had, in fact, two solutions developed by Katrin Stark and Stephen Schäfer. The first one was on well-scoped syntax, and the boilerplate code was generated by AutoSubs2. And the second solution focused on well-typed Bruin encodings, and the boilerplate was sort of proven manually. Both proofs were sort of very much developed in close collaboration with our proofs in Beluga, so they have a very similar structure. So everything can be proven as expected. It's maybe worthwhile noting that substitution and weakenings are functions mapping from positions to terms or positions to other positions. And repetitive proofs are then kind of factored out using proof scripts and Coq tactics. It also led to a way of maybe rethinking AutoSubs. Maybe one should have an AutoSubs 3 where we actually can generate boilerplate code for well-typed syntax automatically. And last, Acta, we used a generic syntax library from Guillaume Mallet. It worked very well for him as an expert user to test and stress test his library. It led, for example, to implementing additional generic results as part of the generic syntax library because they were missing. And the abstractions provided by the library led to very compact proofs. Now, the theory of renaming and substitution is, however, not internalized, and there's no automation. So overall, I think all of us felt it was a success. This benchmark did expose bugs and shortcomings in existing systems. It made libraries and systems more robust. It helped us restructure our proofs, and it helped us to gain a deeper understanding of each approach and how they're actually related. So benchmarks can be great. We would encourage you to explore them. Hopefully we'll see a solution from you. We already saw a solution developed in F*, which is wonderful. But we also hope that some of the considerations and discussions that led to the choice of our benchmark problem helps you to formulate other challenge problems. Of course, this isn't the end. So thanks for listening.